Okay, 37 is a tricky problem. Now, they want us to take region B's, which is defined by this parabola on top and the x-axis on bottom, and the line x equals 2 on the right and the y-axis on the left. So they want us to take region B and revolve it about the vertical line x equals 2, which I didn't think sounded that hard at first here. X equals 2 is this line, so the region is now being spun in this direction right here. All right, so that's what's going on. But as soon as you draw this reflection over here on the other side, you start to realize this is maybe a little bit tougher of a problem than we thought. So our three-dimensional solid is going to look like this, and that'll be a hidden line on the back. And now what's weird here, guys, is that you kind of have this ring going around the solid there, and that would be in the back of it there as well. Kind of looks like a circus tent to me. Now, here's what's really interesting. First of all, we don't have a choice about dx or dy. The axis of revolution is vertical. The slices always run perpendicular to that. This is a dy problem. Now, my next question was going to be circles or washers. What are we dealing with right here? And the answer here is circles, but the radius of those circles, and I should say because there's no gap here between region B and the axis of revolution. But the tricky thing is here, the radii of these circular cross sections, or the disks, that radius is going to change. At the very top, which I think everybody can see, the radius is going to go from here to that curve right over there. But down on the bottom, the radius starts at the axis of revolution and goes all the way out there. Now, I don't want to call these little r and major R because we're not talking washers here. So I'm going to call this lower one radius 1 and this upper region here radius 2. And the big thing here, guys, is that this region has changing boundaries. Right here at x equals 2, this kind of black cut that I'm making right over here cuts this thing into two different pieces. This is basically a cylinder down on the bottom below that black line, and above that, it's basically a type of cone, although not exactly a cone because of the curvature of that parabola. So we're going to have to do this problem in two different ways, everybody. So let's start with something simple. Volume here of the entire region is going to be the volume of part 1, and I'll call that this lower section right here, plus the volume of part 2, which is going to be this upper section up here on the top. Now, let's worry about this bottom part first. We absolutely could do this one just using geometry, but I think we'll go ahead and try to do this one the right way. What I've called R1, guys, the volume of this region down on the bottom, is formed with this radius right over here, and that radius is going to be a constant value of 2. That's not going to change if it moves up or down just a little bit. So let me go a little bit out of order right here, but see what we can do. So volume then, this first volume will be an integral right here of, you have circular cross sections right here, and that area here would be pi times your radius squared, and if the radius is 2, you're just going to end up with 4 pi. That's the radius right there, so I'll just put a 4 pi there. There is no variable, guys, and that's a dy, we said, and the limits of integration, this region begins right here at 0 and ends right here at y equals 2. So that integral should get us the volume of this cylinder down here on the bottom. But then we're going to add to that now another integral that's going to get us the region, or the volume of part 2 of this solid up here on top. And so for R2, that one is going to be variable. It's bordered on the right by the axis of revolution here, x is equal to 2, minus, now it's bordered on the left by this parabola. And boy, I've been doing this a lot lately, so I got it down. X is equal to the square root of y minus 2. That's what borders R2 on the left. So 2 minus the square root of y minus 2, and that can't be simplified at all, so that's going to be R2. And its area formula then is again going to be pi times your radius squared, so that is not going to be as pretty as the last one. Pi times 2 minus the square root of y minus 2 squared. We're not going to try to simplify that at all, guys. So I'm going to go ahead and put the pi, it doesn't matter where you put the pi, probably should put it out in front, and then 2 minus the square root of y minus 2 quantity squared. Integrating with respect to y, and the limits of integration, this begins on the bottom here at y equals 2 and ends up at the peak of that circus big top, which is y equals 6. So I think in one step here, guys, I definitely am going to use my calculator to do this integral, so I might as well go ahead and use it to do this one as well, even though I think that first one is going to be pretty easy. So no reason we shouldn't be able to type this all in one step. Let me go ahead and clear out all this junk I have on my calculator here, guys. And let's go here, actions, let's clear everything out. Okay, and let's do an integral, everybody. So we are going to do menu 43. Okay, and our first integral now is going to go, if I remember this right, from 0 up to 2, and the integrand was just a nice, easy 4 pi, and that was all taken with respect to y. So let me double check that. Integral from 0 to 2, 4 pi with respect to y. Got it. Now let's not hit enter here, guys. We're happy with where we're at, but now we're going to do plus and our second integral. And I think for this one, I put the pi out in front here. So pi and then menu 43. This was an integral starting at 2 and ending, I believe, at y was equal to 6. And now the integrand here was quite a bit more complicated, guys. In parentheses, 2 minus the square root of y minus 2 quantity squared. Okay, so let me start my parentheses, and then 2 minus the square root of y minus 2. Get out of the radical, get out of those parentheses, square all of that, and do this with respect to y. Okay, I think I've got everything typed in there correctly. I believe I remembered the pi in both integrals, which is always a common thing people forget to do. Okay, so let's hit enter here, and we get this answer of 32 pi over 3, which I think is the answer the solutions manual said that we were looking for as well. So 32 pi over 3 cubic units, and there we go, guys. That's our answer to this circus big top problem here in number 37.